Okay, so it's called worksheet 1, but it's definitely not the first worksheet in your new packet, because remember we're throwing some different packets together. This is the beginning of chapter 8, which is the vectors and bearings unit. We're going to be looking at the basics of it here first. We're going to get to the really nasty questions next time we meet. So for now, we're just going to talk about vectors. So vectors are quantities that have both direction and magnitude. So it's not enough to draw like a little, it looks like a ray, but it's really going to be a vector. You're going to have a direction, meaning an angle, and then you're going to have a magnitude, meaning the size of it. Now, magnitude could be a few things. It could be literal distance. It could be speed. When you draw a vector, it's kind of obnoxious because it doesn't really make sense until you put a label on it. So this is one of the few cases where like you definitely have to label your diagrams very carefully. And then, unfortunately, you are going to have to watch me draw. It's going to be really tough. Okay. So an example here they have is the football has both speed and direction. And we've kind of seen this when we looked at parametrics, like the angle at which they kick the football does affect the trajectory of the football, and that's a vector quantity. So there's a couple notes from your book, and this is on your homework, so you don't need to write it down, but maybe pay careful attention here. A boat is traveling 15 miles per hour, and they're claiming, oh, pen, you're going to work? Yeah, no. They're claiming that this has a magnitude of 15 miles per hour, but there's no direction given. So therefore, this is called a scalar quantity. So in your homework questions, if they ask you about this, if there's direction or magnitude, but not both, it's a scalar quantity. So this next one, a hiker is walking 25 paces and then due west. So the fact that they indicated the orientation or the direction that they're traveling means you have both direction and magnitude, and therefore you have a vector quantity. I'll pop with a frowny face. A weight on a bathroom scale. Okay, this one really bothers kids because they're like, well, what do you mean? Weight is a vector quantity because weight is designated as the gravitational pull on your body, right? Downwards towards the ground. So that's kind of a sneaky question because that is technically a vector. All right. But I wouldn't put one sneaky like that on a test, so don't worry about that. So what do you guys think about this one? A car traveling 60 miles per hour headed 15 degrees east of south. That's a vector, right? It has direction and magnitude. A parachute is falling straight down at 12.5 miles per hour. That's also a vector, the falling straight down, the gravitational moment there. A child pulling a sled with a force of 40 newtons. So they gave me the force that they're pulling the sled with, but they didn't tell me like at what angle to the ground. So they're going to claim, I think, yep, this is a scalar. She hid the answers behind that box. I didn't know that last time. Okay. Okay, let's talk about notation. A vector looks like a ray, right? It looks a lot like a ray, but very different, and you can tell it's different because of the context of the problem. So it starts with an initial point, which typically they refer to as A when they're just doing a generic vector, and then a terminal point or an ending point B. So when I'm graphing a vector, obviously they're going to look sloppy because I can't draw anything very well. Sometimes I put a point at the end of it, so that way if someone walks into my classroom and they're looking at my screen, they're going to realize, oh, she just drew a vector. It's not like she's trying to do something weird. The vector itself, mathematically, it's going to behave differently. Like operations on vectors are not the same as what people kind of assume they are. We'll get to the operations next week. But today we're just going to worry about how to draw it, how to notate it, how to read the words. That's kind of the difficult part. So vectors are drawn with the initial point from the origin, drawn in standard position. So there's a lot of like overlap to our work with trig. So from the positive x-axis, it's going to measure counterclockwise when I say like I'm not going to use the word bearing yet because that's a little different. But, 35 degrees with the horizontal, they're referring just like you would in trig class. The magnitude is going to be labeled along like the vector itself. And if it's like 50 miles per hour, you're supposed to write 50 mph, like on the ray looking thing, which is a vector. Sometimes they'll give you a scale. That's what their little thing down here is. It says 1 centimeter represents 5 feet per second. So if you were like diagramming something very carefully, which obviously this is not my forte, they would literally draw it out to scale using a measurement tool. Often in real life, they don't draw them by hand. It's drawn with like computers. But I don't really know what happens in the real world anymore as far as drafting. I'm under the impression that drafting is a little different than what they kind of teach you here. I think it's a little more computer-based than what we see here. Very little of it is hand-drawn drafting these days, but that's not my thing, so I won't speak to that. All right, a scalar quantity has magnitude only, no direction. A vector quantity has both magnitude and direction. So I think we're back on your notes finally. Yes, getting there. So this is from your book. Oh, no, it's not. This is on your notes. If you flip to the back of worksheet 1. A vector, the angle for the vector, the direction, can be written many, many ways, and this is where it gets kind of challenging for kids. So it could be a quadrant bearing. So they'll say things like 30 degrees from the horizontal, or they'll say like something like this, south 35 degrees east. What this means, this particular bearing means, is that you start on the south line, and then you move 35 degrees towards east. So they would have started measuring it from the south line, but they moved 35 degrees towards the east. Now, that measurement itself, we could interpret it a lot of different ways. Like, for instance, they said that's the same thing as heading 145 degrees off of the north line. We'll talk about that in a minute. What else could you call this vector's direction if you measured from the positive x-axis? Anyone have an indicated angle right here? Quick subtraction. Is that 55, negative 55 degrees? Excuse me. So what we're going to learn when we do component form is we're always going to measure the angles off of the positive x-axis, just like you would have done in trig. So, starting at the positive x-axis, moving positively or negatively from there. When we get to component form, that's always how you're going to measure them. Unfortunately, when you guys read a problem, sometimes they present the information in a weird way. Like, for instance, your trig book, I believe, if someone corrects me if I'm not right here, I believe your trig book only used true bearings. Does that sound right, or am I totally lying? You guys remember hearing true bearings were only off of the north line? So a true bearing starts at the north line, and then it measures, this is really weird, they mess with you, they measure clockwise. Now, I think true bearings are very important to certain components of the real world. Like, I'm under the impression, I don't know, because I've never been in an air traffic control tower, but I think when they do like air traffic control and also navigation on the sea, I think everyone measures in true bearings, because that could get really confusing. Like, if the dude next to you says a plane's coming in at a bearing of south 35 degrees west, and then you're like, wait, what? You have to convert it. So if all of them agree to measure as a true bearing off of the north line, it's a little easier for other people to interpret what your answers are. So I'm not saying true bearings are bogus and we should never look at them. I think they're very important in the real world. They're just a little irritating in pre-calc, because when your teacher says, I'm going to give you all sorts of bearings and you got to figure it out, that's part of our challenge today. Okay? So we are going to come back to all that. Here's how you know you have a true bearing, by the way. You might want to highlight this part. They will always measure and write true bearings. They'll either say the words a true bearing of, or they'll write it with 3 numbers like that, 3 digits. So if it has no north, south, east, west, weird letter in the front of it, and it has 3 numbers, that's a true bearing off of the north line. So for instance, true bearing of 25 degrees would be this vector here, where this angle right here measures 25 degrees. Because remember, they read it clockwise on true bearings. Can you give me another way to interpret the direction of that vector? Whoops. See, I can't. This is going to be a bad day. Let me just fix that. While I'm fixing that, did you guys come up with the angle? So if this is a 25 degree angle measuring this way, what's this? Is that 65 degrees? Okay. So they're the same measurement for direction. So you're like, well, why don't you just give me the easy one that's 65? Because I don't direct planes, guys. I don't know what to tell you. I got to teach you all of it, okay? Here we go. This is from your book. They would have used a ruler or protractor and drawn this to scale and giving you a scale measurement. They drew this vector, and it said at a bearing of 030, so that meant a true bearing off of north. And then they measured 30 degrees in the clockwise rotation. They drew the vector. Like they literally would have used a ruler, because at some point in their math they were told that the scale said 1 inch represents 10 feet per second. So since they wanted their vector to be 20 feet per second, how much would they have to have measured to draw this? 2 inches. Yeah, they literally would have had to draw it to scale. Guys, I'm not going to make you break out the rulers for this homework, okay? You're just going to label what they are, I promise. We're not going to do anything crazy. All right, this one, can we just concentrate on the direction of the vector? Don't worry about so much of the scale of the magnitude of it. Look at this label right here. South, 60 degrees west. So that means you start at the south line, which is this guy right here, and then you travel towards the west. So, and then you move towards the west 60 degrees. So that's why they indicated this right here, and they said this is the location of your vector. This is the position of your vector. Can you guys tell me another way I could indicate that angle if I measured from here? How big is this tiny angle right here, this reference angle? That's a 30-degree angle, so if we had 180 plus 30, that would be the same measurement as 210. Yes. Did I do that right? Did I add right? Okay. You don't rotate it. It's just the terminal position that's where it's at. Okay, rephrase your question. I'm sorry. Oh, notate this? So when we do component form, we always have to give the angle measured off of the positive x-axis. So you could have done negative, okay, I could add negative 150. Wouldn't that be the same place? As long as you're measuring from the horizontal. So in a problem, Jenna, they'll say something like from the horizontal. You could, okay, yes, you bring up a good point. There's other, yes, this is annoying, right? So technically speaking, I could have labeled that position a lot of ways. I could have gone true bearing style. I could have gone starting at the west, moving towards the south. Typically for those bearings, they start on the north or south line and then move towards east or west. That's like that's the common notation. I mean, if I ask you how many ways could you indicate that angle, the answer is a lot. True bearing, west of south, the 210, you could go negative 150. They're all the same terminal position. So the point is, I can't give you one answer for that. There's a lot. Now, when we move forward and we do component form, in that question, which is going to be the rest of our unit basically, you have to use the angle off of the positive x-axis. So in this case, you could have used 210 or you could have used negative 150. They're the same. I mean, you can go crazy and call it, you know, plus 360. It doesn't matter as long as it's the same angle measured from the positive x-axis. Okay? And this is why kids don't like bearings, because there's like not that one magical way. So here we go. Let's try. This is on your notes finally, I think. Back to the front, please. It says your vector has a 60-pound force at 125 degrees to the horizontal. So when they write it like that, they're referring to you measuring from the positive x-axis, so like starting here, that's your starting point. And then if you were to measure a normal trig measurement of 125 degrees, just kind of, you don't have to use a protractor, but if we were doing this for realsies, we probably should, but we're going to pretend. Where are we at? 125, so like right here. Okay. So just to be clear, this part is not part of the vector. The vector itself is this red thing I drew, which has an initial spot from the origin and then a terminal point here at the end. But here's what we're going to have to do. You're going to have to label, because I did not use a protractor, you're going to have to label the angle for me. So I'm just going to do this. And then the other thing you're going to have to do is label the magnitude of your vector. So it was 60 pounds of force. So you're going to write 60 pounds along the magnitude, which is just the vector itself. Okay? So that's kind of probably what you suspected we would have done, so that's nice. All right, let's look at number 2. 55 miles per hour, so that's going to be the label for the magnitude. No, it's just the air kicking on. Are you hoping your track meet's canceled? Oh, oh, let the record speak. She wants to do track today. All right, so this is one of the weird ones. Okay, how do we read this? So this is one of those, it's not a true bearing. It's our normal, oops, I wanted black. It's our normal type of bearing where it says to start where? It says, you might want to notate this on your notes a little bit, guys. You're going to start on the south line, and then you're going to move towards the east line 45 degrees. So if you were to start on the south axis and move 45 degrees towards the east, that would be right there in the middle. So the vector itself is what I've drawn in green. You can either call this a 45-degree angle, or you know what? Is there anything wrong with measuring this as negative 40? Okay, this is where we're going to get a little confused. You're just labeling the diagram, so it doesn't really matter where you put this angle. But if I asked you what was the measurement of this angle in normal trig standard form, what would you guys indicate this angle is? Right here. Negative 45 degrees, right? Okay. Because think about your trig unit circle. The way you read it makes a difference for sign. Okay. All right. So anyways, the vector itself, I need you to label the magnitude of 55 miles per hour along the vector. So drawing a vector is not really that exciting. I think just the direction stuff is kind of weird. So let's do one more of these. It does say bearing. Notice it doesn't say true bearing. It also doesn't have 3 numbers. So north 40 degrees west means you start on the north line and then you move towards the west line 40 degrees. So remember, this is north, this is south, this is west, this is east. So starting on the north line and moving 40 degrees towards the west would be like right there. Do that in another color though. So here's my vector. I need to label the angle. We moved 40 degrees westward. And then I also need to label the magnitude, which this time is just 30 meters. Hey, just for funsies, can you tell me what the angle measurement is of that bearing from the horizontal? 130, yep. Here to here is 130. That's going to come into play next, okay? So we got to remember all that trig fun. Alrighty. Get rid of that. Let's move on. We're not going to do a lot of this, but just for vocab, you have parallel vectors, equivalent vectors, and opposite vectors out there in the world. So parallel vectors, this is from your book. I don't think it's anywhere on your notes. Has the same or opposite direction. That's kind of weird. So they could be going, you know, east or west, whatever, but not necessarily the same magnitude. So they kind of look like parallel lines. So A and B and C and E and F are all parallel to each other. They don't necessarily have the same magnitude size. They're not even going the same exact directions, but they're going either the same direction or the opposite directions of each other. Okay, so they are definitely parallel to each other. But equivalent vectors, this is different. Equivalent vectors have the same magnitude and direction. So they should look like twinsies. Everything should be the same. So they're claiming A and C are the only equivalent vectors. Sometimes kids want to tell me that C and E are equivalent vectors, but why are C and E not equivalent? One's going the opposite direction of the other. They don't have the same direction. Opposite vectors would be where they have the same magnitude, but this time they're going in opposite directions. So it's kind of the opposite of equivalent vectors. So in this case, C and E, right? Same magnitude, opposite directions. Oh, and then there's a notation here where it says if you want to indicate that it's opposite, you can just throw a negative sign in front of it. I mean, it makes sense mathematically. Like, yeah, sure, opposite, negative, sure. We're not going to do like hardly any work with that. When we do vector operations on, that probably won't happen until Wednesday next week. we're going to have to just be careful about how we add vectors, how we multiply vectors, how we do scalar vectors, and things like that. All right, we are going to be big believers in what's called component form, okay? Components, rectangular components refer to the horizontal and the vertical components. So this is why I like component form. It only requires me to be able to draw a right triangle. I'm not going to say I'm really great at them, but I'm better than other triangles, okay? So x is horizontal, obviously, and y is vertical. Doesn't that kind of seem like parametric land? X was our horizontal, y was our vertical. Yep, same idea. And you're going to see a lot of comparisons to what we did even in little kid trig with sine, cosine, and tangent, looking at right triangles. Specifically sine and cosine only today. All right, so this question's out of your book. Heather is pushing the handle of a lawnmower with a force of 450 newtons. So they already labeled it. At an angle of 56 degrees with the ground. So notice they put the angle here. They're measuring with the positive x-axis, if you want to think of it that way, but with the ground. And then they're labeling this red leg as x and this blue leg as y, which is probably traditional. Well, you guys would have labeled it that way anyways. So they're wondering, is it on the next slide? Yes. If we could figure out some way to express x and y. Well, guys, if you have an angle, and then you're curious about the adjacent leg and you have the hypotenuse, what trig function do you use when you have adjacent and hypotenuse? That's cosine. So you would have set up the cosine of 56 equals x over 450. Can you solve this for x, please? No, oh, I don't. Sorry. I don't actually want a number. Tell me algebraically what you would do to solve for x. Multiply these together, right? So you'd take 450 and you'd multiply by the cosine of 56. Don't do it. All right, now this next one. How would you find y? Set me up a trig expression that would solve for y. Well, if you have opposite and hypotenuse, we'd be using the sine. And then same thing. Oops, that's no, 450. In order to solve for y, algebraically, you'd cross multiply. So y equals 450 times the sine of 56. So if I look at what I just did, it looks to me like when they wanted to find, why am I going green all of a sudden? When they wanted to find the horizontal component, they took the magnitude and they multiplied it by the cosine of your angle. And the angle was measured with the horizontal axis. And then to find the vertical component, they took the magnitude and they multiplied it by the sine of the angle. I wonder if that's a formula we're going to be given. Yes, it is. Okay. So this question, oh, this is, oh no, it's Jamal. We have Heather right now, right? Okay, we'll get back to Jamal in a moment. So this is them working through Heather's problem. They did go ahead and calculate it. I know some of you guys did too. Did you get about 252 when you expressed that horizontal component? Okay. And then for the vertical component, about 373. And then what they're going to have you do is when I ask you to write the vector in component form, you write vectors like this. So not like ordered pairs, because they're not ordered pairs. They are vectors. So the way we indicate them is we put weird little sideways. Yeah, what? What was your question? You don't what? Oh, you don't have one? You're just really blown away by that lawnmower question? It's a good one, right? Well, let's talk about Jamal. Maybe Jamal will make you guys all excited for vectors. Jamal is pulling the ends of a rope tied to a dinghy with a force of 40 newtons at an angle of 60 degrees with the horizontal. So they've already kind of labeled my diagram for me, which was very nice because that's my struggle. And then we are going to solve for, what colors did I use, red? We're going to solve for the horizontal component and the vertical component. And we're going to do the same thing we just did with, what was her name, Heather? Heather's problem. And I think this is already done on your paper, isn't it? So, exact same way, guys. Cosine of 60 degrees would be x over 50. Now, they use the absolute value. Don't worry about that notation. It's just indicating it's the magnitude of the horizontal piece. And then same thing for the vertical component, but this time it was magnitude times the sine of 60 degrees. They gave approximate answers. And then, what else do they want? The magnitude of the horizontal component is 25 newtons. And the magnitude of the vertical component is about 43 newtons. Okay? So that's just a basic trig question. But I believe right underneath that, they show you this. This is the formula you're going to be needing quite a bit for the next few days of our lessons. When I ask you for any sort of component form, that's component form, okay? The horizontal is r times cosine, and the vertical is r times sine. And they call r the radius. Remember r from Big Kid Trig a while back? The same idea as the magnitude of the vector. Okay. So, we talked about that. The bearings might be a problem as far as reading the bearings. So hopefully we get some good examples of how to read bearings coming up here. Let's see if we can draw this. 7-inch at a bearing of 120 degrees from the horizontal. So, think about how you're going to interpret 120 degrees from the horizontal, and then we just have to label the vector as 7 inches. Little coordinate plane, 120 degrees from the horizontal basically means like a normal trig angle. So, starting here, moving counterclockwise like I normally do in trig. Don't you end up right there? Ish. So here's your vector. You're going to tell me that this angle right here is 120 degrees. You're also going to label the magnitude of this vector to be 7 inches. And they want the horizontal and vertical components. So guys, I'm literally just going to use this formula right here. So remember, it says it's the r times, what comes first for the horizontal? Cosine. And this is the catch right here, guys. The angle is the angle measured from standard position, from the positive x-axis. So that's just 120, okay? The reason we have to use 120 and not the reference angle is because reference angles are not going to put you in the right quadrant and won't give you the right sign. So you just measure normal. And then over here, it's going to be r for the vertical component times the sine of 120. And this time I would like some approximated answers. Tenths place is good. No, one of them should be negative, because if you think about what quadrant you're in, shouldn't your horizontal component be negative? So, and it magically works out. Yay, trig. Did you get negative 3.5? Yeah, and I should label these, huh? Negative 3.5 inches and 6.1 inches. If you leave off the labels, I'm definitely not going to count you wrong. But if for some reason your answer was, like, find the vertical component, I would expect you to say 6.1 inches. In fact, there's a question like that on your test. It says something like this, find the vertical component. So you find the vertical component. All right, that's all we had to do there. Okay, let's interpret this guy. Well, coordinate plane, I'm measuring this vector in this weird notation, north 50 degrees west. So if you start reading at the north line and move towards the west line 50 degrees, you're going to be like right there. Kind of. Can you talk to me, though, about how big, and I don't want the 50-degree angle, guys. I need this angle. What angle is that? 90 plus 50 would be 140. That's the angle you have to use in this component form, because we need to make sure we're in the right... Yes, ma'am. What? I'm sorry. This angle, 90 plus 50 is 140. You good? Yeah. Okay. I'm with you. All right, so the magnitude of this, though, is 2.5 centimeters per hour. Oh, man, I can't fit that. That says centimeters per hour. All right, so components. The horizontal component would be 2.5 times the cosine of the angle. Make sure it's the angle measured from the positive standard position x-axis, 140, comma, 2.5 times the sine of 140. So this time, you should be getting a negative x and a positive y again. Cool. Okay. Negative 1.9 comma 1.6. Is that what you said? Cool. Thank you. Is that the same question you have? I just looked at my old key for my notes. I don't know if I changed the question on yours or mine. Dang it. All right. Well, you guys okay just changing your question then so we don't have to redo that? Is that why Jenna was questioning me? No. Oh, that's okay. We can pretend. So, oopsies, this has changed from notes apparently. Write a little note. Okay. Sorry. So in your notes, it says towards east. Is that the difference? Okay. So the angle would have been different. What would have been your angle from the positive if we went off of what your notes actually said? Would have been a 40-degree angle, right? Because it would have been towards the east 50 degrees, so it would have been 40 degrees from the horizontal up to that vector. All right, fun times. Oh, Billy, then you got to throw a true bearing at me. True bearing, what does that mean? Oh, all right, I hate true bearings. I mean, like I said, they're very useful. I'm sure they make lots of sense to people who use this for realsies, but math teachers aren't those people. True bearings of 140 degrees. So from the north line, and then just to really mess with you, you're supposed to measure clockwise. So moving clockwise 140 degrees. Okay, well that would be like 90. This is too far, 180, so you got to back it up a little, right? So it's like here. So this angle right here is 140 degrees. But that's not going to help me when it comes to using my component form, because my component form is only going to allow me to measure an angle from standard position. Now, it doesn't have to be a positive angle, so can y'all tell me what measurement you could give to this green-looking thing I just highlighted? I think I heard negative 50. Okay. So we're going to use theta equals negative 50. If you wanted to, you could have gone like this. So that would have been like 270. No, I'm sorry. 270 plus 40. I should be able to add that 310. 310 is the same angle. So it's going to work. In fact, you want to have fun and actually type it in. Yes, Jim. Just from standard position. So this to here would be 310. Because this is 40 degrees. That'd be fun. Can we try that out? All right, so, oh, I didn't label my magnitude. My bad, 4 centimeters. So 4 times the cosine of negative 50, and then 4 times the sine of negative 50. And Michaela's having fun typing in 310 to make sure it still comes out the same answers. Okay, it does. That's exciting. All right, 2.6 and negative 3.1. Now, can we all stop and think? Does it make sense to say a vector located yonder would have a horizontal component of positive 2.6? I mean, whatever on the 2.6 part, but it's definitely positive. But the vertical component is negative. Does that make sense to your logical brains? Okay, your vectors should make sense. That's what I like about vectors is, like, you have a lot of knowledge of coordinate planes. You have, moderate knowledge of trig. So when you look at a vector, you should be like, oh, yep, I'm on the right track. I'm in the right quadrant. If some child typed in 140 degrees, because that's the most common mistake on a question like this. They just take the angle and they throw it into the formula. You are not going to get the right answer. For funsies, can someone please type 4 times the cosine of 140? Just so we can show how very, very wrong this is. Something negative, right? 4 times the cosine of 140? Yeah, that's not a negative horizontal value, so clearly they're using the wrong angle. Which you'd think kids would notice on a test, per se. You know how many times I've had to write a note to kids in the past of like, is this a negative x? And then they look at it and go, oh, no. All right, Nadia is pulling a tarp along the ground with a force of 25 pounds direct along the tarp. If the tarp makes a 50-degree angle with the ground, find the horizontal. This is actually not a really hard question, guys. You don't even have to draw a picture. If you want to skip the picture, you can. Because look, 50-degree angle with the ground means this. So your angle, we already have it, it's 50. 25 pounds is the magnitude. So your vector, the horizontal components and the vertical components, let's separate them this time. Because on your test, I think there's a question like this where it just says, what is the vertical component? And that's all I want. So if you get a little crazy and you give me the vector form, that's not going to be right. So horizontal component, please type 25. Oh, by the way, what mode have you been in this whole day? Yeah, you have. Should have started with that, my bad. All right, 25 times the sine of 50 is going to get to the vertical component. And let's label it this time, please. Did you get a 16.1 pounds on the horizontal? Can I get a confirmation on that? Otherwise, we're going off of my key, which is always scary. And a 19.1 pounds? Cool. And clearly we're in the first quadrant there with our little picture, meaning that she's going to be having both positive horizontal and vertical components. Okay, so that's kind of your little intro. I'm going to stop the video there because I don't want to like freak somebody out who's absent today. The next video will cover bearings in its entirety.